Have you ever stood in a city during a power outage? The moment the familiar hum of civilization vanishes, replaced by an unnerving silence. The lights, the very symbols of our progress and safety, extinguish in an instant, plunging our carefully constructed world into a primal darkness. In that moment, we are reminded of a profound and fragile truth. Our entire modern existence is built upon a constant, invisible flow of energy. Every home, every hospital, every factory, every single digital connection that binds us together is utterly dependent on a grid that we demand more from with each passing second. We have stretched this terrestrial network to its absolute limits, drawing power from the earth, the wind, and the atom. But what if the ultimate solution isn't here on the ground with us at all? What if, to secure our future, we need to raise our gaze from the soil beneath our feet to the boundless, sun-drenched emptiness above our heads? What if the greatest power plant humanity will ever build won't be on Earth, but in orbit around it? This is not a fanciful dream. This is the story of a cosmic-scale engineering challenge. The quest to build a planet-sized solar grid, a man-made constellation designed for a single, audacious purpose: to capture the untamed energy of our star and beam it down to power our world forever. It is a project of such staggering scale that it forces us to question the very definition of what is possible. And it begins with a simple, revolutionary thought. Why limit our ambitions to the ground when a literal furnace of unlimited energy hangs in our sky? The sun. It is the engine of our solar system, a gigantic fusion reactor burning with the power of 1 trillion nuclear bombs every single second. The energy it radiates into the void in a single moment is more than humanity has consumed in its entire history. Here on Earth, we receive only a tiny fraction of that power, a mere 1 part in 2 billion. And even that fraction is heavily filtered and frustratingly intermittent. Our atmosphere, the very shield that protects us and allows for life, reflects and absorbs a significant portion of this energy before it even reaches the ground. Then there is the simple yet intractable problem of the Earth's rotation. Night happens. For roughly half of every day, any given solar panel on Earth is rendered useless, sitting in darkness, waiting for the planet to turn. Clouds gather, seasons change, and the efficiency of our best terrestrial solar farms is held hostage by the whims of weather and celestial mechanics. We have built our energy infrastructure around this fundamental compromise. We store energy in batteries. We build redundant power plants. We live with the inherent inefficiency of it all because we've never known another way. But what if we could eliminate the compromise entirely? What if we could place our solar collectors in a location where the sun never sets, where there are no clouds, no atmosphere, and no night? This is the core promise of spaced solar power, or SBSP. The concept is as elegant as it is ambitious. Build colossal arrays of solar panels or mirrors in geostationary orbit, about 36,000 kilometers above the Earth. At this altitude, a satellite's orbital period matches the Earth's rotational period, allowing it to remain fixed over the same point on the equator. From this vantage point, it would be bathed in constant, unfiltered, high-intensity sunlight, 24 hours a day, 365 days a year. This orbital power station would be a true titan of engineering, a structure potentially dozens of square kilometers in area, a glittering mosaic of photovoltaics larger than any city on Earth. This vast collection area would gather solar energy continuously, converting it not into the kind of electricity you find in a wall socket, but into a more focused form, microwaves or lasers. This concentrated beam of energy would then be transmitted wirelessly across the vacuum of space, aimed with millimeter precision at a specific receiving station on the ground, called a rectenna. This rectenna, a large grid-like antenna field, would then convert the microwave energy safely and efficiently back into standard electricity, feeding it directly into our planetary power grid. Imagine a wireless extension cord stretching across a gulf of 36,000 kilometers, delivering a steady, reliable, an inexhaustible stream of clean energy, day and night, rain or shine. It is, in essence, the creation of an artificial, steerable star, a tool that would grant humanity true energy independence. The implications are staggering. We could power entire continents, desalinate oceans to provide fresh water for all, reverse the carbonization of our atmosphere, and fuel the industries of the future without burning a single lump of coal or drop of oil. It would represent the single greatest leap in our energy infrastructure since the harnessing of fire. It would be the engineering equivalent of graduating from a planetary species to a truly stellar one. And yet, when we speak of building such a thing, the mind recoils. The sheer scale of the challenge seems to border on the absurd, a fantasy reserved for science fiction novels. And this is where our investigation truly begins. The central enigma is one of brutal, unforgiving scale. Why does this seem so impossible? Let's begin with the problem of mass. A solar power satellite capable of generating just 1 gigawatt of power, enough for a large city, would, by some estimates, require tens of thousands of tons of material to be placed in geostationary orbit. To power the entire planet, we would need thousands of these stations. We are talking about lifting a mass equivalent to hundreds of aircraft carriers from the surface of the Earth into the highest reaches of orbit. Our current launch technology, the chemical rockets that have served us since the dawn of the space age, are miracles of engineering, but they are also profoundly inefficient and astronomically expensive. The cost to lift a single kilogram of payload to low Earth orbit is still measured in the thousands of dollars. To lift it to geostationary orbit is an order of magnitude more. Lifting the millions of tons required for a global power grid would cost more than the entire accumulated wealth of human civilization. It is a logistical nightmare of the highest order, a barrier of gravity and economics that appears utterly insurmountable. It's like announcing a plan to build a new continent in the middle of the Pacific Ocean, using only rowboats to transport the material. The method is simply not proportional to the task. Then, there is the engineering challenge of the structure itself. How do you assemble, in the zero-gravity, high-radiation environment of space, a delicate structure several kilometers wide? On Earth, engineers contend with wind, weather, and the relentless pull of gravity. In space, they face a different set of adversaries. The unfiltered glare of the sun, creating extreme temperature differentials, the constant bombardment of micrometeoroids, and the degrading effects of cosmic radiation on sensitive electronics and solar cells. This structure would need to be incredibly lightweight to be launchable, yet durable enough to operate for decades with minimal or no human intervention. It would require unprecedented advances in robotics and automated construction, with armies of autonomous drones assembling the station, piece by piece like a colony of orbital insects. Furthermore, it must maintain its precise orientation towards the sun, while simultaneously keeping its transmission antenna locked onto a tiny receiving target on a spinning planet 36,000 kilometers away. Any deviation, any wobble, could cause the beam to miss its target, rendering the entire system useless. The level of control and stability required for such a structure is unlike anything humanity has ever attempted to build. And what of the beam itself? The very idea of transmitting gigawatts of power through the atmosphere from space sounds to the uninitiated like the plot of a supervillain. The immediate questions are ones of safety and efficiency. Could such a beam be weaponized? What are the environmental impacts of pouring that much microwave energy into one spot? The science suggests that the beam's intensity at the rectenosite would be low, comparable to the midday sun, and far from harmful to birds or aircraft passing through it. But the engineering to ensure that safety, to build in foolproof fail-safes that would instantly shut down or defocus the beam in case of any malfunction, is a monumental task in itself. The system must be perfectly reliable, not just for years, but for centuries. And then there's the question of efficiency. How much of the energy captured in space will actually reach the grid on Earth? Every step of the process conversion to microwaves, transmission through the vacuum, passage through the atmosphere, and reconversion to electricity incurs a small loss. To make the entire venture economically viable, the end-to-end efficiency must be incredibly high. It is a chain of engineering miracles, where every single link must perform flawlessly. Faced with these seemingly impossible hurdles, the launch cost, the in-orbit construction, the beam transmission, the sheer economic audacity, it's easy to dismiss space-based solar power as a beautiful but ultimately impractical dream. But here is the central thesis of our investigation. What if the key to solving these problems, the very thing that makes them seem so impossible, is not our limitation, but our greatest opportunity? What if the solution to building on a cosmic scale lies in embracing the cosmic resources that are freely available? What if the answer isn't just about bigger rockets, but about fundamentally changing the way we think about engineering? This is where we pivot from a terrestrial mindset to a cosmic one. We are being invited to stop thinking about the void of space as an obstacle and to start seeing it as the ultimate construction yard, a place of infinite resources and possibilities. This is the promise we will investigate. We will explore the radical new technologies and launch systems that could shatter the cost barrier, from reusable rockets to concepts like the space elevator. We will delve into the astonishing possibility of not launching these materials from Earth at all, but of mining them from the moon and asteroids, using the resources of the cosmos to build our cosmic infrastructure. We will analyze the breakthroughs in robotics and material science that could allow self-assembling structures to build themselves in the vacuum. And we will dissect the physics of wireless power transmission to understand how we can safely and efficiently create this invisible river of energy. This journey is about more than just a single project. It is about a fundamental shift in human perspective. For our entire history, we have been a species defined by the limits of our planet. Our energy, our resources, our very future has been tied to this single, fragile blue marble. The construction of a planet-sized solar grid would be our declaration of independence from those limits. It would be the moment we truly began to harness the solar system, transitioning from passive observers to active engineers of our cosmic environment. So join me as we step into the role of the cosmic detective. Let us assemble the evidence, analyze the blueprints, and confront the impossible challenges head-on. Together, we will investigate the engineering behind the most ambitious power plant ever conceived. And we will ask the ultimate question: is this how humanity finally powers its future? In our introduction, we sketched the blueprints of a dream, a steady, limitless river of clean energy flowing from the heavens. It is a beautiful, seductive vision. But in engineering, dreams are built not with hopes, but with numbers, materials, and a brutal respect for the laws of physics. And it is here, in the harsh light of reality, that our grand project transforms from an elegant concept into a beast of complexity, a challenge defined by a series of seemingly insurmountable obstacles. This is the part of the investigation where we, as cosmic detectives, must set aside the dream and confront the evidence of its impossibility. We must understand the sheer, crushing scale of the forces arrayed against us. The first and most fundamental of these forces, the one that has chained humanity to its home world since the dawn of our species, is gravity. We live at the bottom of a deep, steep, and unforgiving gravity well. Every single component of our orbital power station, every solar panel, every structural beam, every microchip must be forcibly dragged, kilogram by kilogram, out of this well. The physics governing this ascent is described by one of the most beautiful and tyrannical equations in engineering, the Tsiolkovsky rocket equation. In its simplest form, the rocket equation tells us that the change in a rocket's velocity is proportional to the speed of its exhaust and the natural logarithm of the ratio of its initial mass, full of fuel, to its final mass, empty. What this means in practice is a law of savage diminishing returns. To add a tiny bit more payload, you need to add a significant amount of fuel. But that fuel itself has mass, which means you need more fuel to lift that fuel. This terrifying, recursive logic dictates that for a typical chemical rocket, something like 90% of its initial liftoff mass is nothing but propellant. The structure of the rocket itself might be another 6 to 7%, leaving a meager 3 to 4% for the actual payload, a very reason for the journey. It is an act of profound inefficiency, a brute force solution to the problem of gravity. Now, let's apply this tyranny to our project. Let's be conservative and imagine a single satellite capable of delivering 5 gigawatts of power, enough for a few major cities. The estimated mass for such a structure, using today's technology, would be in the range of 80,000 metric tons. For comparison, the entire International Space Station, the largest object humanity has ever assembled in orbit, and a project that took decades, and the combined effort of multiple nations to build, weighs about 450 tons. Our single-power satellite weighs as much as 177 international space stations. To lift this mass into orbit, we would need the most powerful rockets ever built. A SpaceX Falcon Heavy can lift about 26 tons to a geostationary transfer orbit. The upcoming Starship aims for perhaps 150 tons to low Earth orbit, which translates to much less for the high-energy flight to geostationary orbit, even with the most optimistic future projections for a super heavy launch vehicle. Let's imagine a capacity of 50 tons to the final orbit. To launch our single 80,000-ton satellite, we would need 1,600 individual launches. 1,600 launches of a rocket class that does not yet exist. And that is for just one satellite. To replace a significant portion of Earth's current energy consumption, around 20 terawatts, would require thousands of these satellites. The total mass to be lifted into orbit would be in the tens of millions of tons. The number of launches required would be in the hundreds of thousands. The sheer industrial scale of such an undertaking is without precedent. It would mean launching several massive rockets per day, every single day, for decades. The cost, even with optimistic future launch prices of, say, $500 per kilogram, would be in the tens of trillions of dollars, a figure that rivals the entire GDP of the planet. Gravity, then, presents our first great wall. It is a barrier not just of physics, but of pure, crushing economics and logistics. It tells us that with the tools we currently possess, building this grid isn't just hard, it's an economic impossibility. But let us assume for a moment that we could somehow solve the launch problem. Let's pretend we have a magic carpet to ferry these millions of tons to their destination, 36,000 kilometers above the Earth. Our challenges, I'm afraid, have only just begun. We now face the second great adversary, the environment of space itself. We call it space, but it is not empty. It is arguably the most hostile and unforgiving construction environment imaginable. The first hazard is radiation. Without the Earth's protective magnetic field and atmosphere, our satellite is completely exposed to the raw, unfiltered violence of the cosmos. It is constantly bombarded by a hailstorm of high-energy particles, protons and electrons trapped in the Van Allen belts, heavy ions from distant supernova known as galactic cosmic rays, and periodic, violent blasts of radiation from solar flares. This radiation is a relentless agent of decay. It slams into the crystalline lattice of our photovoltaic cells, creating microscopic defects that degrade their performance over time. A solar panel that is 30% efficient on day one might be only 20% efficient after a decade of this assault. This requires either constant replacement and repair, a logistical nightmare in itself, or the use of advanced, radiation-hardened materials that are heavier and more expensive, which feeds back into our initial launch problem. Electronics must be shielded, often with layers of dense materials like aluminum or tantalum, adding still more mass to our payload. Then there is the problem of thermal cycling. Our satellite is in a constant battle between fire and ice. The side facing the sun can heat up to over 150 degrees Celsius, while the side in shadow can plunge to 150 degrees below zero. This 300-degree temperature differential creates immense mechanical stress. Materials constantly expand and contract, a process that over millions of cycles leads to metal fatigue, microfractures, and eventual structural failure. To manage this, the satellite would need a complex and heavy thermal regulation system, including vast radiators to dump waste heat into the vacuum of space. These radiators would need to be enormous, adding yet more square kilometers of surface area and, you guessed it, more mass. This is not a passive structure. It is a living, breathing machine that must constantly fight to maintain its own equilibrium in an environment that is actively trying to tear it apart. Finally, there is the physical threat of impacts. The space around Earth is not pristine. It is littered with millions of pieces of orbital debris, pent rocket stages, dead satellites, and tiny flecks of paint from previous missions, all traveling at speeds of over 28,000 kilometers per hour. At these hypervelocities, a 1-centimeter aluminum sphere impacts with the kinetic energy of a small car crashing at highway speeds. A fleck of paint can gouge a crater into solid metal. Our power satellite, with its surface area measured in square kilometers, is not just a target. It is a continent-sized bullseye in a cosmic shooting gallery. Shielding the entire structure is impossible due to the mass penalty. Therefore, it must be designed to be resilient, to absorb thousands of tiny impacts over its lifetime without catastrophic failure. This requires sophisticated design, redundant systems, and most likely, a fleet of autonomous repair drones, constantly patching holes a level of robotic technology and autonomy that is still in its infancy. Now, we come to the third great challenge, the very heart of the system, the transmission of power. It is one thing to generate petawatts of energy in orbit. It is another thing entirely to deliver it safely and efficiently to a specific point on the ground, 36,000 kilometers away. The chosen method is a focused beam of microwaves. The fundamental challenge here is a physical phenomenon called beam divergence or diffraction. Any electromagnetic wave, no matter how well collimated, will naturally spread out over distance. The degree of this spreading is inversely proportional to the size of the transmitting antenna. To keep the beam focused on a receiving retina that is, say, 5 kilometers in diameter, from a distance of 36,000 kilometers, the laws of physics dictate that the transmitting antenna in space must have a diameter of at least 1 kilometer. Think about that. We are not talking about a simple satellite dish. We are talking about a phased array antenna, an intricate electronic system with a diameter equivalent to the height of 3 Eiffel Towers stacked end to end. Assembling and operating such a structure with the required phase precision is an engineering challenge of the highest magnitude. And the precision required does not end with the antenna's construction. The pointing accuracy of this beam is absolutely critical. From 36,000 kilometers away, the 5-kilometer receiving station is an incredibly small target. An aiming error of just 1 arcsecond, that's 1/3600th of a degree, would cause the beam to drift by over 170 meters on the ground. A tiny error of just a fraction of a degree would miss the station entirely. The satellite's attitude control system must be perfect. It must constantly compensate for minute forces, like the pressure of solar wind, the gravitational nudges from the moon and sun, and the vibrations from its own internal systems. It must maintain this impossible level of accuracy, not for a few minutes or hours, as a telescope might, but continuously for decades. The fail-safes required are equally daunting. The system must be able to detect any aiming malfunction in microseconds and instantly defocus the beam to a harmless, low-intensity state. The software governing this system would be the most complex and reliable code ever written, because the consequences of failure are simply too high. So we are left with this mountain of challenges. A launch problem that defies our economic reality, an orbital environment that actively seeks to destroy what we build, and a power transmission system that requires a scale and a precision that borders on the miraculous. Each of these problems, taken alone, represents a monumental feat of engineering. Taken together, they form a compelling, evidence-based case for why this project should remain firmly in the realm of science fiction. This, then, is the puzzle. We are not just fighting gravity or radiation or distance. We are fighting scale itself. The case against seems closed. In the last phase of our investigation, we built a formidable case against our own ambition. We stood before the titans of physics, gravity, radiation, distance, scale, and found our project wanting. The verdict seemed clear: impossible. But a good detective knows that the scene of the crime often holds the very clues needed to solve the case. The evidence presented against us was, in fact, an incomplete picture. We were analyzing a cosmic problem through a terrestrial lens. Now we change our perspective. We stop looking at space as a hostile void we must conquer and start seeing it for what it truly is: an environment of boundless resources and unique physical properties that, if understood correctly, can be leveraged into powerful engineering advantages. This is the phase where we gather our counter-evidence. We will now investigate the clues hidden in plain sight, the physical realities of the cosmos that offer a pathway through the impossibility. Our first and most important clue is the very reason for the project: the sun itself. But we must look at it now, not as a distant goal, but as a raw, concentrated resource. On Earth, we are starved for sunlight. The energy that reaches the ground is a pale imitation of what exists just a few hundred kilometers up. The first number a cosmic engineer must memorize is the solar constant. It's the measure of the sun's power at the top of Earth's atmosphere, and it's approximately 1,361 watts for every square meter. Compare that to the best you can hope for on the ground, in the middle of a desert, at high noon on a clear day, which is about 1,000 watts per square meter. That's an immediate advantage of over 36% more power density. But this is just the beginning of the story. The true advantage isn't just in the intensity, it's in the consistency. Here on the surface, the day-night cycle is our master. Add in clouds, atmospheric dust, and seasonal tilt, and a terrestrial solar panel's capacity factor, the measure of how much power it actually produces over a year, compared to its maximum rating, is often a paltry 15% to 25%. It's an inherently unreliable source. Now consider our satellite in geostationary orbit. It is bathed in that full 1,361 watts per square meter for over 99% of the year, with only brief, predictable eclipses by the Earth's shadow occurring around the equinoxes. This results in a capacity factor of 99% or higher. When you do the math, this means that a single square meter of solar panel in space will generate, over the course of a year, at least 5 to 6 times more energy than the exact same panel on Earth. This is a staggering multiplication of efficiency. The very problem of space, its distance, provides the solution to the problem of intermittency. Furthermore, the light in space is pure. Our atmosphere acts like a filter, absorbing and scattering certain wavelengths, especially in the ultraviolet and infrared parts of the spectrum. In space, the full, unadulterated solar spectrum is available. This allows engineers to design highly advanced, multi-junction photovoltaic cells that are like gourmet chefs, able to capture energy from many different flavors of light, pushing theoretical efficiencies far beyond what is practical on Earth. So, our first clue is this: the energy source in space isn't just slightly better, it's overwhelmingly superior, a fire hose of power compared to the dripping faucet we have on the ground. Our second clue is found in the very nature of the environment we once called hostile, the vacuum of space. On Earth, every engineering project is a battle against our own environment. We fight corrosion from an oxygen-rich atmosphere. We fight friction. We fight the unpredictable violence of wind and weather. The vacuum of space, while dangerous to unprotected life, is an engineer's paradise. It is the most pristine, stable, and predictable industrial environment imaginable. Consider manufacturing. In a vacuum, there is no oxygen, no water vapor. Metals do not rust or tarnish. This opens up entirely new industrial processes. Techniques like cold welding, where two perfectly clean pieces of metal will fuse together on contact without any heat, become simple and reliable. Thin film deposition for electronics and solar cells can be done with a purity impossible to achieve on Earth. It is, in effect, the ultimate clean room, and it is the size of a solar system. Moreover, the absence of an atmosphere means there is no wind, no rain, no storms, no seismic tremors. This stability is a profound engineering gift. On Earth, a large structure like a bridge or a skyscraper must be designed with immense strength and rigidity simply to withstand wind loads and its own weight. In space, you can construct vast, gossamer-like structures, delicate and sprawling, that would instantly collapse on Earth. Imagine a solar collector made of a reflective film only a few microns thick, stretched out over a kilometer. On Earth, a light breeze would shred it. In space, it can maintain its shape for centuries, moved only by the gentle, predictable pressure of sunlight itself. This clue tells us that our terrestrial intuition about what a structure should look like, solid, heavy, rigid, is wrong. Space invites us, even demands us, to design in a completely new language of lightness and fragility. This leads directly to our third, and perhaps most mind-altering clue, the principle of microgravity. We called Earth's gravity a tyrant, a great wall, and it is. But once we escape it, its absence becomes one of our most powerful tools. In orbit, an object has no weight. It is in a constant state of freefall. The primary design driver for nearly every structure on Earth, the need to support its own mass against the relentless pull of gravity, simply vanishes. This is a complete paradigm shift in structural engineering. The millions of tons of compressive strength we build into earthly structures become almost entirely unnecessary. In space, the dominant forces are tension and momentum. This means that a space-based structure doesn't need to be a rigid, compressive behemoth like a skyscraper. It can be a tensile structure, more like a spider's web or a suspension bridge, where lightweight cables and beams are held in tension. This allows for an incredible reduction in mass for a given size. The 80,000-ton satellite we described in Phase 1 was based on a terrestrial design philosophy. An engineer thinking in the language of microgravity could design a structure with the same power output for perhaps a fraction of that mass. We can build bigger with less. The very concept of a planet-sized solar grid becomes less daunting when you realize the grid might be more like a network of shimmering, ultra-lightweight films and tensegrity structures than a solid, heavy platform. Microgravity is also a gift to manufacturing. On Earth, gravity causes heavier elements in a molten alloy to settle, introduces defects in growing crystals, and makes it impossible to create perfectly uniform materials. In zero-G, you can mix materials that would never combine on Earth. You can grow flawless crystals for next-generation electronics, and you can forge alloys of unparalleled strength and purity. Space isn't just a place to assemble parts made on Earth. It's a place to create entirely new materials that are themselves a solution to our engineering problems. These first three clues, constant energy, the perfect vacuum, and the freedom of microgravity, are powerful. They change the rules of design and efficiency, but they do not, by themselves, solve our greatest hurdle, the tyranny of the rocket equation, the crushing cost of lifting millions of tons from Earth. And for that, we must turn to our fourth and final clue, the one that truly unlocks the cosmic scale, the resources of the solar system itself. Our investigation has so far assumed that everything we need must be shipped from our home planet. This is the equivalent of the first European explorers believing that any new colony in the Americas would have to be supplied forever with food and timber from Europe. It's a fundamentally unsustainable model. The truth is that we are not at the bottom of the only gravity well. We are simply at the bottom of the deepest one in our neighborhood, just next door on our moon, and in the thousands of near-Earth asteroids that cross our planet's orbit lie all the raw materials we could ever need. This concept is called in situ resource utilization, or ISRU, and it is the key to breaking the shackles of the rocket equation. Let's examine the evidence. The lunar regolith, the dusty soil of the moon, is composed of roughly 45% oxygen by mass, bonded into its rock and mineral structure. It is also rich in silicon, the primary component of glass and solar cells, and metals like aluminum, iron, and titanium, the very building blocks of industrial civilization. Near-Earth asteroids are even more diverse. M-type asteroids are essentially giant, flying mountains of high-grade iron-nickel steel. S-type asteroids are rich in silicate materials. And the most valuable of all, C-type asteroids are laden with water ice and carbonaceous compounds. Water is the oil of the solar system. It can be separated into hydrogen and oxygen, the most powerful chemical rocket propellant we know. It provides life support for crews and is a crucial industrial reagent. The critical piece of evidence here is the energetic cost. To lift 1 kilogram of material from Earth and deliver it to geostationary orbit requires a massive amount of energy. To lift that same kilogram from the surface of the moon to GO requires roughly 22 times less energy. The moon's gravity is only 1/6 that of Earth's, and it has no atmosphere to create drag. For many asteroids, the energy cost is even lower, hundreds of times less than from Earth. This is not an incremental improvement. It is a fundamental disruption of the entire economic and logistical model. It means that for the cost of launching one large, fully equipped robotic mining and processing facility from Earth to the moon, you could then, in theory, generate millions of tons of raw materials, metals, silicon, oxygen, propellant that never have to fight their way out of Earth's gravity well. This clue suggests that the solution to the launch problem isn't just better rockets. It's to stop launching the bulk material altogether. We must stop thinking of our project as something we build from Earth and start thinking of it as something we build in space. With space resources, the solar system is not just the location of our power plant. It is also our mine, our foundry, and our factory. These are the clues the cosmos provides. A source of endless, concentrated energy. A perfect, stable construction environment. A realm free from the constraints of weight. And a floating treasury of raw materials. The case for impossibility is beginning to crumble. We now have the evidence for a new theory. The question is no longer, is it possible? But how do we connect these clues to solve the case? We stand at a critical juncture in our investigation. In one hand, we hold the case for the prosecution, a list of seemingly insurmountable challenges that label our project an economic and engineering fantasy. We have the tyranny of gravity, the hostility of the space environment, and the terrifying precision required for power transmission. In our other hand, we hold the detective's notes, a collection of powerful yet disconnected clues. The raw, unfiltered power of the sun, the perfect industrial conditions of the vacuum, the design freedom of microgravity, and the untapped treasury of resources floating in our cosmic backyard. The two sides stand in opposition, a chasm of impossibility separating them. This is the moment where we bridge that chasm. This is the Eureka moment. The flaw in our initial investigation was a deeply ingrained terrestrial bias. We assumed Earth had to be the factory, the mine, and the supply depot for a cosmic project. We were trying to solve a cosmic-scale problem with planetary-scale thinking. The ingenious connection, the technical thesis that resolves this entire puzzle, is this: to build on a cosmic scale, you must first build a cosmic-scale industry. The solution to making space-based solar power viable is not to launch it from Earth, but to create a self-sufficient, self-expanding industrial ecosystem in space that can build it, and thousands of others like it, using the energy and resources that are already there. We are not just building a power plant. We are seeding the solar system with an industrial revolution. Let's revisit our first great adversary, the crushing launch cost, the tyranny of the rocket equation. We calculated that lifting the required millions of tons from Earth would bankrupt our civilization. The problem is not the rocket equation itself, that is a law of physics, but our stubborn insistence on fighting it from the bottom of the deepest, most punishing gravity well in the inner solar system. The clue of in situ resource utilization, ISRU, is the key that unlocks this prison. Our thesis proposes that instead of launching the millions of tons of steel, silicon, and aluminum, we launch something far lighter and far more valuable: information. We launch the seeds of industry. The first step is to send a relatively modest payload to the moon, a starter kit of highly advanced autonomous robotics. This initial package, let's call it the Genesis unit, would contain robotic miners to excavate the lunar regolith, solar arrays to power the operation, a chemical processing plant to refine the regolith into its constituent elements, and a versatile robotic factory capable of 3D printing and assembling complex components. The Genesis unit's first directive is not to build a power satellite. Its first directive is to replicate itself. Using the aluminum, iron, and silicon it extracts from the lunar soil, the Genesis unit would begin fabricating the components for a second Genesis unit. The one factory becomes 2, the 2 become 4, the 4 become 8. This is the power of exponential growth, a force far more potent than any chemical rocket. We are bootstrapping an entire industrial base on the moon, and the vast majority of its mass is sourced locally. We have traded the brutal, linear logistics of launching everything from Earth for the elegant, exponential logistics of self-replication. Once this lunar industrial base reaches a critical mass, its directive shifts from replication to production. The same factories that built copies of themselves now begin churning out the components for our solar power satellites. Lightweight structural trusses from lunar aluminum and titanium, kilometers of wiring from extracted metals, and most critically, vast arrays of solar cells printed from the abundant lunar silicon. We have effectively moved our factory off-world. But how do we get these components from the moon to their final assembly point in geostationary orbit? We certainly don't use rockets. Instead, we use another piece of elegant physics, an electromagnetic catapult or mass driver. This would be a long, linear accelerator built on the lunar surface. Using electricity generated by its own solar farms, the mass driver would accelerate cargo containers full of satellite components to lunar escape velocity, launching them on a precise trajectory into space. It's a clean, efficient, and purely electric launch system, with the moon's low gravity and lack of atmosphere making it vastly more efficient than any Earth-based launch. The tyranny of the rocket equation has been sidestepped. We have solved the problem of mass, not with bigger rockets, but with smarter industrial architecture. Next, we confront the hostile environment of space. We described it as a chaotic arena of radiation, extreme temperatures, and micrometeoroid impacts. Our thesis argues that this environment is only hostile to things that were not designed for it. The solution is to embrace a new design philosophy, one native to the cosmos, enabled by the clues of microgravity and the vacuum. On Earth, our structures are heavy and rigid because they must constantly fight gravity. In the weightlessness of space, this design language is obsolete. Our power satellite would not be a single, solid plate. It would be a vast, modular, gossamer structure. A gossamer being a term for something light, thin, and delicate. Think more like a kilometer-scale spider web than a steel platform. This design, enabled by microgravity, would be incredibly mass-efficient and resilient. If a micrometeoroid severs one truss, its load is instantly redistributed among thousands of others. The system is designed for graceful degradation, not catastrophic failure. But what about the constant radiation that degrades the solar panels? Our terrestrial mindset sees this as a fatal flaw requiring heavy shielding. Our cosmic industrial mindset sees it as a simple maintenance problem. With our lunar factories able to produce solar cells from common silicon as easily as a terrestrial factory produces plastic bottles, the panels themselves become a cheap, replaceable commodity. The satellite would be serviced by a fleet of autonomous maintenance drones, also built on the moon, that constantly crawl its structure, identifying degraded panels and replacing them with new ones. The satellite would be in a state of constant self-renewal. Its lifespan would no longer be limited by the durability of its components, but would be indefinite. We have transformed the problem of radiation from a materials science challenge into a solvable, automated logistics operation. This same principle applies to the other environmental hazards. The vacuum, once a challenge for containing atmospheres, becomes the perfect environment for deploying large, ultra-thin radiators to manage thermal stress and for performing maintenance without the risk of corrosion. The constant threat of debris is managed not by adding tons of armor, but by making the system intelligent and self-repairing. We are no longer building a static, passive object to endure the harshness of space. We are building a dynamic, robotic ecosystem that lives and thrives within it. The design philosophy shifts from one of a fortress to one of a living organism, constantly adapting and regenerating itself using locally sourced materials. Finally, we arrive at the challenge of the power beam itself, the need for a kilometer-wide transmitter with an impossible pointing accuracy. This challenge, too, dissolves when viewed through the lens of our new thesis. Assembling a kilometer-wide, delicate antenna on Earth is unthinkable, but assembling its thousands of lightweight, modular components in the zero-G vacuum environment of a dedicated orbital assembly yard is a task perfectly suited for robotics. Components launched from the moon via the mass driver would be captured at a Lagrange point or in a high orbit, where automated drones would piece them together. The structure, free from the strain of gravity, can be assembled with a precision that would be distorted by its own weight on Earth. The problem of its immense size is a problem of terrestrial thinking. In space, it is merely a matter of logistics and robotic choreography. The solution to the terrifying pointing accuracy lies in making the system a closed loop. A low-power laser beacon would be sent up from the center of the receiving rectana on Earth. This beacon provides the orbiting satellite with a perfect, unwavering target. The satellite's control system would not be aiming at a set of calculated coordinates. It would be actively locking on to this beacon, making real-time, microsecond adjustments to keep the power beam centered. The beam itself, being a phased array of thousands of small emitters, offers another layer of ingenious control. We don't steer the beam by physically moving a kilometer-wide structure. We steer it electronically, by minutely adjusting the phase of each individual emitter. It is a purely digital, solid-state steering system, offering a level of speed and precision mechanical systems could never achieve. And this provides the ultimate fail-safe. It's not a single beam that can be accidentally misdirected. It's a composite signal. In the event of any malfunction, a loss of the guide beacon, a software glitch, a hardware failure, the default state is for the emitters to fall out of phase. The beam instantly and passively decoheres, its energy spreading out harmlessly over a vast area, its intensity dropping to negligible levels. The system is designed to be intrinsically safe. The very physics that creates the beam also provides the mechanism for its instant dissipation. The case is closed. The impossible has been resolved. Every great challenge we identified in Phase 1 has a direct and elegant solution found in the clues we gathered in Phase 2. The launch cost is overcome by ICE-RU and exponential robotic manufacturing. The hostile environment is tamed by a new language of microgravity design and constant automated self-repair. The transmission problem is solved by in-situ robotic assembly and intelligent, closed-loop control systems. This is the power of the cosmic detective approach. The problems and solutions were there all along, two sides of the same cosmic coin. We simply had to learn to look at the universe not as outsiders, but as engineers ready to use its native rules to our advantage. For the entirety of this investigation, we have operated as detectives and engineers, piecing together a technical thesis from the scattered clues of the cosmos. We have proven, at least in principle, that the impossible is possible. But a blueprint, no matter how ingenious, is not the finished structure. A thesis is not the revolution. Now, we transition from the role of engineer to that of historian of the future. We will lay out the practical, step-by-step roadmap of how this grand endeavor could unfold, not in a single magical leap, but as a multi-generational project, a technological cathedral built over the course of a century. And then we will dare to look beyond the construction, to contemplate the world that inherits its power, to understand the true legacy of building a star for the Earth. This is not just how it would be built, but why it would change everything. Our grand construction project begins not with a colossal rocket, but with a series of quiet, deliberate, and intelligent first steps. The first decade of this endeavor is Phase 1, establishing the foothold. The objective is singular: to prove the core principle of our thesis, in situ resource utilization. On the Moon, it begins with a fleet of robotic surveyors sent to the lunar poles, specifically to the rims of craters like Shackleton, where peaks of eternal light offer near-constant solar power, and the deep, permanently shadowed floors may hold deposits of water ice, a resource of immense value. Once the prime location is selected, the first true construction package is launched from Earth. This is our Genesis unit. It is not a sprawling factory, but a compact, brilliantly engineered seed of industry. It contains a small team of solar-powered robotic rovers for mining, a modest processing unit for extracting raw silicon, aluminum, iron, and oxygen from the regolith, and a highly versatile 3D printing and assembly bay. It is accompanied by a small, human-tended habitat, a lighthouse on the lunar shore, where a crew of 4 to 6 highly skilled engineer astronauts will oversee and troubleshoot this nascent industrial ecosystem. Their primary mission is not to build the power grid, but to prove that they can make a brick, and then a wire, and then a fully functional solar panel created entirely from the gray dust beneath their feet. The success of Phase 1 is not measured in gigawatts, but in grams of lunar-sourced aluminum in the successful test of the first Lunacrete structural beam. It is the moment humanity stops being a visitor to the Moon and becomes a resident, a manufacturer, a builder. With the principle proven, we enter Phase 2, the industrial bloom spanning the next 2 decades. This is the era of exponential growth. The Genesis unit, having successfully fabricated its first components, begins its primary directive, self-replication. Using the materials it mines, it builds another Genesis unit. Then, the two of them build 2 more. This slow, then sudden expansion transforms the small outpost into a sprawling industrial complex. A lunar Silicon Valley emerges, dedicated to the mass production of solar cells. A lunar iron range develops, processing metals for structural components. All of this is powered by the very solar arrays it produces, a clean, self-sustaining industrial loop. During this phase, construction begins on one of the project's key enabling technologies, the first electromagnetic mass driver. This is a monumental undertaking in itself, a linear accelerator stretching for kilometers across the lunar plains. Simultaneously, a second robotic front opens. Prospecting missions are sent to nearby, easily accessible near-Earth asteroids, identifying resource-rich targets for future exploitation. The human presence on the Moon grows from a handful of pioneers to a permanent settlement of hundreds of engineers, scientists, and roboticists. By the end of this phase, the Moon is no longer a desolate landscape. It is the primary industrial hub of the Earth-Moon system, capable of producing thousands of tons of refined materials and finished components per year. Now, we enter Phase 3, First Power, a period of roughly 20 years where the vision finally becomes a visible reality. The lunar mass driver is complete. With silent, electric precision, it begins launching cargo pods filled with satellite components into a high-orbit assembly point. Here, in the stable, weightless environment of space, a new kind of factory awakens, a vast, free-flying robotic shipyard. Fleets of assembler drones, fabricators, and welders themselves, built on the Moon, converge on the delivered components. They are the weavers of this new constellation. They unfurl the gossamer-thin mirrors. They snap together the lightweight trusses. They wire together the fields of solar panels. We watch from Earth as a new star begins to take shape in our sky, a glittering web of human ingenuity. Back on Earth, the first receiving antenna is constructed, a vast grid of antennas covering 100 square kilometers of remote desert. It is a quiet, passive structure, a catcher's mitt waiting for the pitch. Then the day arrives. The first solar power satellite, SPS-1, is fully assembled and tested. Its antenna locks onto the pilot beacon from the ground, and with the flip of a switch, a silent, invisible beam of pure energy bridges the 36,000-kilometer gap. On the ground, meters begin to spin. The grid surges with clean, constant power from space. This single moment is the payoff for 50 years of work. It is the proof, broadcast to the world in the form of billions of watts, that the system works. The final stage is Phase 4, the global grid, the century-long process of scaling up to power the entire planet. With the industrial pipeline perfected, the process becomes routine. The lunar factories operate with the efficiency of a planetary assembly line. A new, more advanced solar power satellite is completed every few months. More antennas are built around the globe, floating offshore, in deserts, on plains, creating an interconnected, resilient global energy network. The price of electricity plummets, becoming almost too cheap to meter. And it is here, as the construction becomes a steady hum in the background of civilization, that we must turn our gaze to the true legacy of this monumental work. For we have not just built a power plant, we have rebuilt our world. The first and most immediate legacy is the healing of our planet. The completion of the global grid marks the definitive end of the fossil fuel era. The geopolitical power of oil-rich nations evaporates, replaced by a new paradigm of shared energy abundance. The primary engine of climate change is shut down, not just neutralized, but actively reversed. With limitless clean energy, massive-scale carbon capture becomes economically trivial. We begin to pull our centuries of carbon pollution out of the atmosphere. Ocean desalination plants, powered by dedicated energy beams, and global water scarcity, allowing us to turn deserts green and restore ecosystems. The Earth, scarred by our industrial adolescence, is finally given the chance to breathe again. This ushers in an economic renaissance. Energy is the base layer of any economy. When it becomes abundant and nearly free, the cost of everything it touches, manufacturing, transportation, computing, food production, plummets. This is the dawn of a post-scarcity civilization. Poverty, at least in the material sense, becomes a solvable problem. Any community, anywhere on the planet, can have the power to build modern infrastructure, purify its water, and run advanced industries. It is the greatest engine for global equality humanity has ever conceived. But the legacy extends beyond the economic and into the very fabric of our civilization and our identity. This project, by its very nature, would require a level of international cooperation unprecedented in human history. It would be a common goal, a shared work that would bind nations together in a way no treaty or threat ever could. It would become a symbol of what we can achieve when we see ourselves not as competing tribes, but as a single planetary species. And it would fundamentally change our relationship with the sky. For all of history, we have looked up at the stars as distant, untouchable points of light. Now, among them would be a new constellation of our own making, a shining testament to our ambition, visible to every person on Earth. The sky is no longer a ceiling. It becomes a part of our extended home, a realm of human activity. This is the final exam for becoming a Type 1 civilization on the Kardashev scale, a species that has achieved mastery over the energy resources of its home world. And in passing this test, we unlock the next level. The vast industrial infrastructure we built in space, the lunar factories, the asteroid mines, the orbital shipyards, does not get decommissioned. It becomes the foundation for humanity's true expansion into the solar system. Building a colony on Mars, a research base on Europa, or a mining operation in the asteroid belt is no longer a series of breathtakingly expensive one-off missions. It is a straightforward logistical task for an industrial machine that is already in place. We have built the highway. Now we are free to explore. This is the ultimate legacy, a change in perspective. We would cease to be a species clinging to the shore of our cosmic ocean and would become, at last, its navigators. We would have inherited the stars, not as objects of worship or poetic fancy, but as tools and as a destination. The child who looks up at the sky in this future would not just see the moon, they would see the minds that built their world. They would not just see the stars, they would see the lights of their own civilization shining back at them. A constant, brilliant reminder that there are no longer any limits. Our investigation is now complete. We began with a simple question born of terrestrial limitations. How could humanity possibly build a power plant the size of a planet in the hostile void of space? We stood at the base of a mountain of impossibility, its peaks shrouded in the mists of unimaginable scale and cost. We meticulously documented every reason this project should fail, every law of physics that stood as a guard at the gate of our ambition. We spoke of the tyranny of gravity, a force that demanded a price in mass and energy so high it would bankrupt our world. We mapped the dangers of the cosmos, the unending assault of radiation, the brutal extremes of temperature, and the silent threat of hypervelocity debris. We calculated the astonishing precision needed to bridge the void with a beam of pure energy, a task requiring a stability and accuracy that seemed to border on magic. The case for impossibility was robust, logical, and thoroughly convincing. It was a case built on centuries of human experience as a planetary species, a case that concluded that the sky was, and would always be, a limit. But then, our investigation pivoted. We adopted the mindset not of a terrestrial builder, but of a cosmic detective. We began to look at the evidence not as a list of obstacles, but as a set of rules for a new and grander game. We found the clues hidden in plain sight. We found that the unfiltered, unending sunlight in space was not just a source of power, but a torrent of energy so vast and reliable, it made our terrestrial sources seem like fading embers. We discovered that the vacuum we so feared was, in fact, the most pristine and stable industrial cleanroom imaginable, a place where we could build with a delicacy and scale impossible in our turbulent atmosphere. We learned that the absence of gravity was not a strange anomaly, but a profound liberation for design, allowing for the creation of vast, lightweight structures that were more cloud than steel. And most critically, we uncovered the great secret that the solar system was not empty, but was a treasure house of resources, that the moon and asteroids held all the metals, silicon, and volatiles we would ever need, waiting for us in gravity, wells far shallower and more forgiving than our own. These were the clues, and with them, we built a new case. Our eureka moment was the realization that these two cases, the impossible and the possible, were not in contradiction. The solution to the challenges was encoded within the challenges themselves. The key that unlocked the puzzle was the thesis of a self-replicating space-native industry. We understood that the way to defeat the crushing cost of Earth's gravity was not to fight it, but to sidestep it entirely by sourcing our materials from the cosmos. We saw that the way to survive the harsh environment of space was not to build an impregnable fortress, but to create a dynamic, self-repairing ecosystem that used the sun's own energy and local materials to constantly renew itself. We deduced that the way to build and aim a kilometer-scale antenna was to embrace the freedom of microgravity and the precision of robotics, assembling it in the very environment it was designed for. We connected the clues to the crime, and in doing so, we demonstrated how the impossible becomes plausible, and how the plausible, with time and will, becomes engineered reality. We then laid out the roadmap, a multi-generational plan that saw this grand vision not as a single, fantastical leap, but as a patient, deliberate process of seeding an industrial revolution in space. One that would not only power our world, but heal it, uniting our species and opening the solar system for our children. This journey, from a seemingly absurd premise to a coherent technical plan, teaches us a fundamental lesson about the nature of the word impossible. In the lexicon of science and engineering, impossible is rarely a final verdict. More often, it is a declaration of our own limited perspective. To the ancient world, crossing an ocean was impossible. To the medieval mind, flying through the air was impossible. To the scientists of the early 20th century, reaching the moon was impossible. Each of these impossibilities held true only until a new perspective was gained. A new set of physical principles was understood and masterfully applied. The architects of the age of sail did not defy the winds and currents. They learned to harness them. The pioneers of aviation did not conquer gravity. They mastered the principles of lift and aerodynamics. The engineers of the Apollo program did not break the rocket equation. They solved it with breathtaking ingenuity. The construction of a planet-sized solar grid falls into this same noble tradition. It is not about a war against the cosmos. It is about a deeper partnership with it. It is about the uniquely human capacity to look at the fundamental laws of the universe and see not just constraints, but a set of tools, a divine blueprint waiting for an architect. This brings us to the very heart of what engineering is. It is the bridge between what is and what can be. It is the disciplined application of creativity to the constraints of reality. A project of this scale forces us to think on a time scale that transcends individual lifetimes. Like the artisans who laid the first stones of a cathedral, they knew their great-grandchildren might complete. This endeavor requires a form of civilizational patience. It asks us to invest in a future we ourselves may not fully inhabit, to believe that the work itself, the act of striving for a goal so audacious, is a worthy legacy. It forces us to act not as individuals, but as a link in a chain of generations. It is the ultimate expression of the human first principle, for its final aim is not the glorification of technology, but the liberation of human potential on a planetary scale. The goal is not the satellite. The goal is the world it creates, a world free from want, a world of clean air and blue skies, a world where the accident of a child's birthplace no longer determines their access to the energy that fuels a modern life. Our investigation concludes, but the story is far from over. The purpose of this journey was not to present a final, immutable plan to be executed tomorrow. It was to engage in an act of disciplined imagination. It was to show that the future is not a far-off country we discover, but a territory we design and build. The physics is sound. The resources are waiting. The engineering challenges, while monumental, are challenges of scale and will, not of fundamental possibility. We live in a unique and privileged moment in history. We are the first generation to truly understand the cosmic resources at our disposal, and we are the first to possess the fledgling robotic and technological tools to begin, in some small way, to reach for them. The question, therefore, is not whether it can be done. The question is whether we will choose to do it. Will we continue to be a civilization that quarrels over the dwindling resources of a single world? Or will we become the civilization that learns to harvest the infinite bounty of its solar system? Will we remain defined by the limits of our cradle, or will we finally embrace the legacy of the stars that is our birthright? The final truth our investigation has uncovered is that the greatest barriers are not technical. They are the limitations we place on our own ambition. The blueprints are all around us, written in the language of orbital mechanics and material science. The choice is ours, to look down at the ground or to look up and begin.